OpenFOAM is an open source CFD solver package, unlike any other commercial solver packages such as ANSYS Fluent and COMSOL. The main difference being it is open source, i.e. it is free of cost. It is licensed under general public license, which means you can reference it in any of your research papers or any of your research without any cost. Open source is owned by OpenFOAM Foundation. It was created by Mr. Henry Weller in 1989, and it was released as an OpenFOAM project in 2004. Foam being open field operation and manipulation. OpenFOAM is entirely written in C++, which ensures high performance computing. By that, I mean it ensures parallel processing, multi machines, multi nodes, which will help you with your solving. OpenFOAM is a well-developed CFD code package. It has a wide range of applications, and they keep on adding new features every year with each version. OpenFOAM has many of the advantages over their competitors. Namely, OpenFOAM has a very user-friendly syntax, and it is easier to understand the mathematical operators, easier to understand the field variables that are defined. OpenFOAM is very well documented. You can check out their website or any other web resources that you can find. I'm assuming that many of you are well versed with any of the programming languages, low level programming languages such as C, C++, or anything. In these programming languages, it is the duty of the programmer or user for handling memory management using pointers and such. OpenFOAM does memory management automatically, which is a huge plus. OpenFOAM also handles unstructured meshes well. By this, I mean for any of your complex geometries, you need not create complex meshes or ensure structured mesh. Unstructured meshes do well. The main disadvantage that OpenFOAM has is its absence of a GUI. Its competitors such as ANSYS Fluent or COMSOL have the advantage that you can choose an option, a button on your screen, and can change particular values. But in OpenFOAM, you have to specify of your control variable. OpenFOAM solver package has a steep learning curve as well. By this, I mean you need to be well versed with the programming language structure and basic CFD, basic fluid dynamics. The other disadvantage that OpenFOAM has is its slow development. By this, I mean OpenFOAM is managed by a few developers from the OpenFOAM Foundation, and they roll out each new version of OpenFOAM in a year or two. And this development process takes some time. OpenFOAM is compatible with most of the OSs or majority of the OSs that we have operating systems. Since Windows is the most commonly used operating system, Linux is provided for in Windows using the WSL or Windows Subsystem for Linux. Recently, they released the WSL2 version. It is supposedly faster. Even though preferred environment is Ubuntu Linux, I would preferred environment is Linux since the source code is written for the Linux environment, but it doesn't matter. OpenFOAM simply needs a Linux terminal to install on the Linux environment, and this Linux terminal can be accessed or installed on any of the OSs at the moment, namely Windows, Mac OS, any of the Linux distributions. The most recent version from openfoam.org is OpenFOAM 8, and it can be installed on Windows on the 18.04 Linux distribution, not the 20.04. This is a very simple example of the environments. In Windows, you can see you use the Windows subsystem for Linux WSL, and you can see the files that are in this particular directory as a list on the terminal. In contrast to that, with Ubuntu, you get a more physical feel. You can select this with a mouse. Overline of what we are going to go through today. I'll briefly talk about the introduction to simulation structure that is followed in OpenFOAM. Then we'll go through a brief introduction to compressible flow and turbulence in OpenFOAM. Then I will try to explain an example problem for the compressible flow. And then any questions you guys have, we'll tackle them. So a brief introduction to OpenFOAM. OpenFOAM follows a particular file structure in a working directory in which you will store all your control files, and the post-processing is also done through this directory. we will go through meshing, initial conditions, and solvers and post-processing. This is a neat example of a flow in a curved pipe. If I can talk about it just a minute, what's happening here is flow goes through from the left-hand side right here, and there is an injection of secondary flow that happens here. This is an example of compressible flow. So this is a basic layout of any CFD study. Initially, we need to decide on the domain, the geometry, and then we solve for the mesh, whichever way we seem fit, structured, unstructured, so on and so forth. After checking for the meshing parameters, if your mesh is proper, in the sense that your orthogonal quality, skewness, etc. are all good, then we set the initial conditions, after which we set for the solver. We choose our solver, choose its controls, and then solve the equations based on the solution's requirement, set the initial time, end time, delta t, and so on and so forth. After which we post-process. And during post-processing is where we validate our study using an example experimental study or any published study. Let's talk about mesh. Mesh is a very crucial part of any discretization study. Mesh is defined on a geometry as a set of points, coordinates. Now, this is done mostly on the cell faces or cell centers based on the type of solver that you are using. And these coordinates are then mapped onto a matrix to solve for the governing equation. All mesh must satisfy certain criteria, and we need to ensure that it is a valid, continuous, and accurate mesh. Plenty of validity constraints are checked for, namely, as I mentioned, orthogonal quality, skewness. These constraints are to be checked for before running for the numerical solution. OpenFOAM defines mesh in 3D regardless of the dimensions of your study, i.e. if you are conducting a 2D study, you still need to define one cell into the third dimension. OpenFOAM mesh is bounded by arbitrary polygonal faces, i.e. each cell can have unlimited number of faces. General structure of mesh in OpenFOAM is defined in a folder called polymesh. This is situated in the constant folder, and we will go through this later. OpenFOAM offers a great freedom for mesh generation and manipulation. The check mesh function in OpenFOAM is especially useful, as we will see later. BlockMesh is a powerful tool. It's a meshing function. It is a powerful tool developed in OpenFOAM. BlockMesh decomposes the domain geometry into a set of multi-hexahedral blocks. The edges defined may be straight lines, arcs, or splines, and BlockMesh is controlled from the BlockMesh dict file situated in the system folder. I know it might sound confusing at the moment, but I will walk you through the process. For instance, this is an example of the BlockMesh dict. Here, the geometry is made for a rectangular block, and as we can see here, a function that we refer to is convert to meters. What this does is it converts, it is for unit conversion. OpenFOAM inherently adopts SI unit systems, so length is considered in meters. And right here, we can specify the conversion factor. For instance, for inches, you can just write 0.0254. And right here, we are using centimeters. Here we specify our vertices for our geometry. And as we can see, the Z direction is also specified. These vertices are then clubbed into a box of grades 20 by 20, i.e. 20 divisions in X direction and 20 divisions in Y direction, and 1 division in the Z direction. Simple grading is basically a multiplier, in the sense that 20 times 1, 20 divisions in X, 20 times 1, 20 divisions in Y. And you can use this to increase the number of cells in the particular direction. We don't have any curved edges or splines in this particular geometry, so we will not define any. And right here in boundary, we are defining our boundary conditions as well. Top wall right here is considered as a moving wall, and it is given the type wall. In cavity flow, the top wall moves at a constant velocity, and the interaction of the moving of this wall is then studied over the flow inside this cavity. A good example to visualize this particular phenomenon would be, let's say, If the skin of an aircraft's wing is taken away, there are several holes inside on top of the wing, and flow over that will simulate a flow in a cavity. This is a good example of the functions of blockMesh. In here, this is a blockMesh for symmetric NACA 0012, I think, airfoil. We split the domain geometry into different blocks and give grading for each of these blocks. Physical properties. Properties such as viscosity, turbulence properties such as defining the turbulence model, combustion properties such as species molar weight, fuel type, equivalence ratio, etc. are all the examples for physical properties. In OpenFOAM, these physical properties are stored in dictionaries, which are named properties or whose names end with properties. These files are located in the constant folder. All of these files contain the control variables or values for the properties, field properties, which are required for the simulation. Namely, the kinematic viscosity, species molar weight, etc. can be defined in these dictionaries. Files such as transport properties, turbulence properties, thermophysical properties, etc. are all such examples, as we can see. In the working directory for the cavity flow in constant folder, we have transport properties. And as I mentioned earlier, polymesh. The polymesh folder is created inside the constant folder, and it has the data for your mesh, boundary faces, and so on, so forth. These are some of the examples of physical properties. Namely, for turbulence properties, we define Reynolds averaging simulation RAS, and the RAS model being K omega SST. For turbulence in a laminar flow, we define it as laminar. For thermophysical properties, and right here, as you can see, transport properties, we define our viscosity, its units, its value, and so on and so forth. Initialization is essentially the start of your simulation, i.e., for more common studies, at time t is equal to 0, the values of your properties. These are the conditions with which you initiate your study. Initial pressure, temperature, velocity, etc. are the primary concerns. As the study gets more complex, we need to define more properties as required. For instance, for turbulence, we need to define K, omega, epsilon, and so on and so forth, and for combustion as well. In initial conditions, there are the initial conditions are situated in the 0 folder, aptly named since most of the study started time t is equal to 0. And in each of the initial condition files, there are 3 main entries: dimensions, internal field, and boundary field. Dimension specifies the dimension of the property. Internal field specifies the values of the field that are specified, and these can be uniform or non-uniform. Boundary field is where you define your boundary conditions, and properties such as turbulent values and combustion properties, Z, Y, equivalence ratio, fuel properties, etc. can be defined in the 0 folder. As an example, for the cavity flow, as we can see in 0 folder, we have pressure and velocity. As we can see right here on right hand side for the U and P file, first we have the dimensions. In dimensions, you can see 0, 1, -1, and all zeros. These values correspond to the power of base units of measurements, namely M, L, T, I, theta, N, and J. These are the base units of measurement: mass, length, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. Right now in CFD, we are just concerned with the mass, length, and time. And next we can see internal field. Velocity and pressure are defined in the internal field as uniform, and their value is 0. In the boundary field, we can see the upper wall, moving wall, is given the value of velocity 1 in the x direction. It is a fixed value. And for the walls, the other values are set as no slip and 0 gradient. A solver is a set of algorithms which are implemented to approximate the solutions to governing equations. Each type of study comes under a domain of these CFD areas that are mentioned. And each of these areas have their own solvers with flux and time schemes. These solvers, these algorithms are well developed at this point. Believe it or not, an exact solution to the Navier-Stokes equations is still a mystery to us. Exact solution. It even has a price of $1 million, namely the Millennium Prize. And these prizes are laid out by the Clay Mathematics Institute since 2000. What we try to do in CFD is simply discretize the domain and solve for approximate solutions to the NS equations. Supports these following CFD areas: steady, unsteady, compressible, incompressible, multi-phase, DNS, and so on and so forth. Solution is controlled through the file called control.dict. These are the areas of physics that are supported in CFD for OpenFOAM. And for this particular case, compressible flow, these are the three solvers: rhoCentralFoam, PeopleFoam, and SimpleFoam. In OpenFOAM, the numerical schemes for terms such as derivatives in equations, the governing equations, are defined in the file called fvSchemes. And for solving of equations, for their tolerances, for the algorithm implemented, these are all defined in the fvSolution file. These files and these sorts of algorithms, solutions, are very well documented and can be found in any of the internet resources. OpenFOAM itself has a website where they share their source code, and it can be accessed from there. You are really encouraged to glance over them and understand the complexity behind them and try to make sense of it. But don't feel overwhelmed. These have been in development since a long time, and it might feel as if you are lost, but you will get a hang of it. This is an example of a fvSolution and fvSchemes. As we can see right here, the fvSolution file has solvers for your field properties, pressure, P final, and velocity. Right here, if you see as an example, pressure has a solver called PCG. PCG is a preconditioned conjugate gradient solver. This uses a set of LDU decomposition of matrices, lower diagonal and upper matrix decomposition. And the algorithm for this is well documented, and you can go through these. The tolerance, relative tolerance, and other values are specified as well. For time discretization, we use the piezo scheme, and you can see its control variables right there. In fvSchemes, we define the mathematical operator algorithms. In our governing equations, we have the d by dt terms, gradient terms, Laplacian terms, and so on and so forth. Each of these terms require a particular algorithm through which they are solved. And again, don't feel overwhelmed. OpenFOAM has a vast number of examples, test problems, which you can go through and really understand which particular field or area of CFD requires these solvers for each of the scheme. These are all situated in the system folder for your running directory, namely the blockMesh control deck, fvSchemes, and fvSolution. All flows in nature are inherently compressible. We assume that low speed flows are incompressible since the compressibility effects are negligible. They are not as inherent. And the major reason for why we assume incompressible flow for low speed flows is to reduce complications that we need to consider for in order to solve the governing equations. If we take a look here, these are the governing equations. Any flow that has density changes is considered compressible flow. Any flow that has a density changing from its in to out is considered compressible flow. In nature, these effects are not negligible after Mach number 0.3. So after a particular speed greater than 0.3, we need to consider the flow as compressible. OpenFOAM in itself has a vast array of applications for simulating high-speed flows, as we saw before. These are the fundamental equations. Few of the examples of compressible flow are written here, as you can see. Compressible flow in itself is very sought after, and it is the most required skill for CFD engineer. In industry, for instance, let's take an example. For any CFD engineer who works on pipe flows, In industries, if you are working on pipe flows, you need to really understand compressible flow. The transport of, let's say, particular gases, particular fuels through these pipes are essential, and the safety has to be ensured so as to not cause a catastrophe. Compressible flow comes into play right here. Areas such as vehicle designs, your car design, reduction for drag in cars, car engine design, the IC engine design, in aircrafts, wing design, body design, or your engine design, compressor, turbine, combustor, all require compressible flow. One of the examples right here. This is a cross section of an IC engine. This is a velocity contour. Now, I want to briefly talk about one of the solvers from the compressible flow solvers in OpenFOAM. Right now, I want to make it very clear. Please do not be scared. I simply want to show you the complexity that goes through behind development of these solvers. If you don't understand, do not worry. I just want to briefly go over the structure of the solver. rhoCentralFoam is a density-based compressible flow solver. It is based on central upwind scheme of Kurbanov and Tadmor. rhoCentralFoam solves for nonlinear convection diffusion equations. These equations are not tied to a specific eigenstructure of the problem. rhoCentralFoam provides for more precise information of local propagation speeds. By this, what I mean is in high-speed compressible flows, we encounter discontinuous waves, namely shock wave and rarefaction waves. Each of these waves have local propagation speeds, and these differ from your flow velocity. These are to be tracked using the Gaussian equations, and rhoCentralFoam provides for a precise information of these local propagation speeds. This particular solver also maintains high resolution, and it is independent of the order 1 by delta t. By this, I mean under the set value of Courant number, you can change your delta t value as much as possible under the limit of your Courant number, and the solution will still maintain high resolution, high accuracy. I briefly want to go over the method used for solution in rhoCentralFoam. Initially, so as I said earlier, in meshing, the geometry is discretized, and the cell centers or the face centers are taken as the coordinates. And on these coordinates, the field variables, your density, temperature, velocity, are all mapped. And these are set into matrices. And as we spoke before in the fvSchemes and fvSolution slide, the d by dt and gradient solvers have their own particular named solvers. These matrix operations are performed on each of these equations based on the particular algorithm that we chose. I say that very loosely. Initially, the continuity equation is solved explicitly. From here, we get the value for density. Then we solve the momentum correction equation. This correction equation does not contain any viscous terms. We consider only the inviscid terms. After which, a prediction equation for momentum is chosen for a small pulse, and it is used to update velocity, which then is solved for in the velocity correction equation, which considers the diffusive terms, and we get final value of velocity. After which, we choose the stress tensor values, and an explicit approach is used to solve for these equations. After which, the momentum equation, for the momentum equation, the again inviscid part of energy equation is solved again as a predictor. So the way these solvers work is initially we do not have the value for the next time step, and we assume or predict a set of values for these field variables, and later we correct them using a corrector step. Again, we can go through these later, but this is a simple procedure. After solving this inviscid part of energy, temperature is then updated using this relation, and there is a temperature correction equation, and this is solved implicitly to get the final value of temperature From this final value of temperature, we update pressure through the perfect gas law, P is equal to rho RT. In the rhoCentralFoam solver, the time discretization is done, and the time scheme chosen is a Runge-Kutta scheme. Runge-Kutta scheme has several orders. You can choose the order of the scheme. You can choose the order of the RK scheme based on the requirement of your study, requirement of your solution, the amount of accuracy that you require for time discretization, namely for slower than real time, faster than real time analysis. By that I mean anything that is not happening at clock time or anything that is less than 1 second is considered faster than real time analysis. And for time schemes, the higher order schemes are implemented when your delta T is especially very low, where you require high resolution, i.e. your field variables change drastically over very short period of time. rhoCentralFoam is unlike any other solver in CFT. The structure of solution is as follows. Pre-processing values are set in the 0 folder. The field variables such as velocity, pressure, temperature, density, etc. are all specified there. Mesh is made using blockMesh or snappy hex mesh based on the requirement of case. Snappy hex mesh is majorly used for 3D cases, and blockMesh is relatively simpler for simpler studies. And in the same mesh, you define your geometry using the vertices as we discussed before. In CFT, there are particular cases where you need to patch certain field variable values onto your geometry, i.e. for the previous example, IC engine. In IC engine, where after your fuel is injected, you need to spark the fuel air mixture. This can be done in CFD using patching. At that particular time step after fuel is injected, you can define a particular temperature value at the base of your piston cylinder configuration, and that will simulate your spark. This can be done in OpenFOAM in the set fields dict file. The solver controls are all defined in the control dict file as we saw earlier in system folder. In here, you can specify your start time of solution, end time of solution, the right interval, and so on and so forth. And in OpenFOAM, since there is a lack of GUI, post-processing is done through another open source data visualization software called ParaView. ParaView is also written in C++. Many of you who use Python for, I'm not sure how many of you use this, but for data analysis in Python, ParaView is a very good tool.